Hi there, and welcome to Tech with Shaping Pixel. In this video, we're diving into Part 3 of the AWS Certified Advanced Networking Specialty ANS-C01 full crash course. The exam is divided into 4 domains: network design, network implementation, network management and operation, and network security, compliance, and governance. Each domain covers specific skills, from designing global architectures to securing network traffic and ensuring compliance. Network design focuses on optimizing user performance, designing DNS solutions, integrating load balancing, and creating routing strategies across multiple AWS accounts and regions. Network implementation tests your ability to connect on-premises networks to AWS using site-to-site VPNs and Direct Connect, and to automate network infrastructure. Network management and operation covers maintaining connectivity, monitoring traffic, and optimizing for performance and cost. Network security, compliance, and governance assesses your ability to secure networks using AWS WAF, Shield, firewalls, and encryption, as well as monitoring and auditing network activity. Apart from this crash course, cover the preparation question and answers from our YouTube channel at Tech with Shaping Pixel. Review the official AWS exam guide, understand each domain's requirements, and practice with AWS networking tools like CloudWatch, VPC Flow Logs, and Route 53. Good luck on your certification journey. The OSI Model and TCP/IP Protocol Suite. Welcome! This course on the OSI Model and the TCP/IP Protocol Suite designed to support your preparation for the AWS Certified Advanced Networking Specialty Certification. Whether you are new to AWS networking or looking to deepen your expertise, you are in the right place. This course provides a high-level introduction to the OSI Model and the TCP/IP Protocol Suite. Our goal is to help you understand the foundational networking models as well as practical concepts like building and configuring jumbo frames. By the end, you will be ready to tackle networking questions on the updated AWS Certified Advanced Networking Specialty exam. We will explore the OSI and TCP/IP networking models, focusing on how they relate to AWS networking services. You will learn about jumbo frames and their configuration. The course concludes with an in-depth review of the IPv4 protocol, including classless interdomain routing or CIDR, IPv4 reserved addresses, subnetting, and addressing modes such as unicast and multicast. This course is ideal for those with experience designing, implementing, and operating complex AWS and hybrid networking architectures, especially if you are preparing for the AWS Certified Advanced Networking Specialty exam. All AWS cloud concepts will be explained from the ground up, ensuring you are fully prepared to sit the exam. Let's get started. The Open Systems Interconnection Model, or OSI model, is a framework introduced in 1984 by the International Standard Organization. It defines how different networking protocols interact in a stack of 7 layers, making it easier to understand and design networks. The TCP/IP model, also known as the Internet Protocol Suite, is the foundation for most modern networks, including the Internet. Developed in the 1970s by the United States Department of Defense, it predates the OSI model. Unlike the OSI model's 7 layers, the TCP/IP model has just 4. These are the application layer, transport layer, internet layer, and network layer. The application layer combines the OSI's application, presentation, and session layers, while the network layer merges the physical and data link layers. As data moves down the TCP/IP stack, each layer adds its own header. The application layer handles user data. The transport layer creates segments or datagrams. The internet layer forms packets with IP addresses, and the network layer produces frames with MAC addresses for local delivery. Protocols like HTTP, SMTP, and FTP operate at the application layer. The Transmission Control Protocol, or TCP, ensures reliable delivery, while the User Datagram Protocol, or UDP, prioritizes speed. The Internet Protocol, or IP, manages logical addressing, and Ethernet handles physical connections. Understanding TCP/IP is essential, as it powers everything from web browsing to email. Its layered approach and robust protocols make global communication possible, forming the backbone of today's interconnected world. Let us break down jumbo frames and why they matter for your network performance. The maximum transmission unit, or MTU, is the largest packet size, measured in bytes, that a network connection can handle. The bigger the MTU, the more data you can send in a single packet. Standard Ethernet frames typically support a 1500-byte MTU, which is the maximum size for most internet connections. Jumbo frames, on the other hand, can support up to 9,000 bytes, allowing you to send up to 6 times more data in one go. This is especially useful for high-performance environments. Because Ethernet frames have a fixed size header, sending larger frames means less overhead and more efficient data transfer. Jumbo frames are ideal for dedicated private networks, server clustering, backups, and distributed file systems like the Network File System, or NFS. Amazon EC2 instance types such as C3, M4, and R4 support jumbo frames for enhanced throughput. However, jumbo frames are not suitable for every scenario. Applications sensitive to latency, like voice over IP, may experience delays. Always ensure all network equipment supports the larger MTU before enabling jumbo frames. Let us demonstrate the impact of jumbo frames in a cloud environment. We will compare two network paths between virtual machines, one using a standard maximum transmission unit, or MTU, of 1500 bytes, and another using jumbo frames with an MTU of 9,000 bytes. Our setup involves two virtual private clouds, or VPCs, each with two subnets. We launch an EC2 T2.micro instance in each subnet, and each instance has two elastic network interfaces, or ENIs. The first ENI, ETH0, is set to an MTU of 1500, while the second, ETH1, uses an MTU of 9000. Policy-based routing ensures traffic flows through the correct interface. We used a CloudFormation template to build this environment. After setup, we SSH into the receiver instance and start a netcat listener on port 10000. On the sender instance, we run scripts to send exactly 1 megabyte of data, first over ETH0 with standard frames, then over ETH1 with jumbo frames. Packet captures are taken for analysis. The results are clear. Transferring 1 megabyte with jumbo frames results in significantly fewer packets and higher throughput compared to standard frames. This demonstrates the efficiency and performance benefits of using jumbo frames for large data transfers in cloud networks. IPv4, or Internet Protocol Version 4, is the backbone of Internet addressing. Standardized in the early 1980s, it uses a 32-bit binary scheme, providing about 4.3 billion unique addresses. This logical addressing operates at the Internet layer of the TCP/IP model. An IPv4 address consists of 32 binary bits, grouped into 4 octets separated by dots. Each octet ranges from 0 to 255 in decimal, making addresses like 192.168.10.1 easy to read. This format is called dotted decimal notation. Originally, IPv4 used address classes A, B, and C to divide networks and hosts, but this system was inefficient. In 1993, classless interdomain routing, or CIDR, replaced it, allowing flexible subnet masks and more efficient use of address space. Certain IPv4 ranges are reserved for special purposes. For example, 127.0.0.1 is for loopback testing, while 10.0.0.0, 172.16.0.0, and 192.16.0.0 are private addresses, not routable on the public internet. Subnetting divides a network into smaller segments, improving performance and security. It uses subnet masks like 255.255.255.0 to define network and host portions within an address.